Hello there, Mr. Sutton here, bringing you the AB Calculus 5-6 Extra Practice Number 2 solutions on trapezoidal rule. On this problem, they want us to approximate the area under this function over this interval with 5 subintervals using the trapezoidal rule. So we're going to start by putting together a table with the correct x values, and then we'll come up with some y values, and then we'll go trapezoidal on this. So here's our table. We've got 5 subintervals. That means we're going to have 6 endpoints to work with. And if we're going with 5 of these over a distance of 10, that means each subinterval is going to have a distance of 2. So we're starting at -4, and then that's going to go until -2, and then 0, and then 2, and then finally 4 and 6. So now we're going to plug all of these into this function to get the y values that go with it. So let's see here. I'll just do this all on the calculator. So I've entered my f of x function in the y equals in y1, and I'm going to go to table set, second window. We're going to start at -4, and we're going to go up by 2's for my delta table, and then let me just do a second graph, and there's my values. So we've got 7, 6, 5, 4, 3, 2, and so on and so forth. So there we go. So this is just straight out of the table on my grapher. And now for trapezoidal rule, I'm going to say that the integral from -4 to 6 of f of x is approximately equal to the following. So for our first trapezoid, we've got 7 plus 6 over 2 times a height of 2. So there's what that first one looks like. And then after that, we've got 6 plus 5 over 2 times a height of 2. And then 5 plus 4 over 2 times a height of 2. 4 plus 3 over 2 times a height of 2. And then finally 3 plus 2 over 2 times a height of 2. So you can leave it unsimplified, or if you want to simplify it on the calculator, you can do that. I'm actually going to go ahead and do that now. So I just started entering this in, and I noticed that we have a 2 in the denominator and the numerator for all of these fractions. All those 2's are going to cancel. So really, for this particular problem, just to do it quickly on the calculator, I'm just adding all the numerators. So we have 7 plus 6 plus 6 plus 5 plus 5 plus 4 plus 4 plus 3 plus 3 plus 2 all comes out to 45. So there we are. For this problem, I want to approximate the area under this function using the trapezoidal rule. We're going from 1 to 6 with 5 subintervals. So that means that each of these has to have a base of 1, or a height of 1, I guess, if you're using trapezoids. Let me set up a table, and let me figure out exactly what I need for my endpoints. So I'll do the x values first, and I know I need 6 entries if I'm doing 5 subintervals with trapezoids. So I've got, we're starting at 1, and then we've got 2, 3, 4, and then 5, and then 6. And now just plugging all of these in to get the y values that go with it. And let's see here. We could do this on the calculator, but I think we don't need one for this. So 3 over 1 is going to be 3. 3 over 2, that's going to be, we'll say 1.5. 3 over 3 is 1. 3 over 4 is 0.75. 3 over 5, that's going to be 0.6. And then 3 over 6 is going to be 0.5. Setting up our trapezoidal rule, we can say the integral from 1 to 6 of f of x is approximately equal to, and now we have to add these two things, divide by 2, and multiply by the height. So we have 3 plus 1.5, those are the bases, over 2, because we're averaging them, times the height of 1, the distance between 1 and 2 there. For the next one, we've got 1.5 plus 1 over 2, times a height of 1. These are all going to have a height of 1, so it's really just the numerators that are going to change. For the next fraction, we've got 1 plus 0.75 on top, then it's 0.75 plus 0.6 on top, and then 0.6 plus 0.5 on top. You can leave this unsimplified and it's numerically equivalent to the right answer, or you could do it in the calculator, which I'm going to do now. Now, as I prepare to do this on the calculator, one thing I do notice is that all of these have a denominator of 2. And I mean, we don't need to multiply everything by 1. I think I can do that in my head just fine. But let me start by just writing a 1/2 using fancy fraction mode or otherwise. And now let me just open a parentheses, basically factoring a 1/2 out of all of these. And I'm just going to add the numerators now. So we have 3 plus 1.5. 3 plus 1.5. Let's see, plus 1.5 plus 1 plus 1 plus 0.75 plus 0.75 plus 0.6 plus 0.6 plus 0.5. Close my parentheses. Hope for the best. 5.6. There we are. On this problem, I want to find the area under this curve, or at least approximate it, with the trapezoidal rule. We have an interval from -4 to 6 with 5 subintervals. So let me set up a table and at least figure out what x values I'm using for this. So since I'm going a distance of 10 in 5 subintervals, that means that I need 2 for the distance of each of those trapezoids, the horizontal distance anyway. So we're starting at -4, and after that we've got -2, 0, 2, 4, and 6. And then plugging all of those in now, I'm going to do this on the calculator. So I'll start by entering my function f of x as y1 and my y equals, just so I never have to write all that again. And then let me do a table for this to make it a little bit easier. So second, table set. Let me set up my table. So I'm starting at -4. I'm going with a delta table of 2. And if I go to second graph, that pulls up my table. So at -4, I have an output of 13. And after that, it's 5, 1, 1, 5, and 13. So kind of easy to remember. We had a 13, a 5, a 1, and then there's some symmetry going on apparently. Hey, we'll take what we can get. So now I have to actually set up all my trapezoid areas. I'm going to say integral of f of x from -4 to 6 is approximately equal to, and here's my first trapezoid. We have a base of 13 plus a base of 5 divided by 2 times a height of 2 to get from -4 to 2. So there's that first setup. And then after that, we have 5 plus 1 over 2 times 2, 1 plus 1 over 2 times 2, 1 plus 5 over 2 times 2, and 5 plus 13 over 2 times 2. You can leave it unsimplified, or you can plug it in the calculator and see what it all comes out to. In fact, I probably don't even need a calculator for this. I mean, all these 2's are going to cancel out, so I'm really just adding the numerators. And let's see here, in the numerators, we've got 13 plus 5 is 18, plus another 6 is 24, plus 2 is 26, plus another 6 is going to be 32, plus another 18 is going to be really exactly 50. Well, that's kind of neat. For this problem, I want to approximate this integral using this table and the trapezoidal rule. So I can say that this stuff is approximately equal to the following. Setting up my trapezoid areas, I have the bases of -1 and 2 being added together. We'll divide that by 2 to average them, and then we'll multiply by a height of 3 to get from 0 to 3. So there's my first trapezoid area. After that, I've got -2 plus -1 over 2 times a height of, it looks like 3 again. And then we've got -1 plus 0 over 2 times a height of, this time from 6 to 7, we have a height of 1. And then finally, we have 0 plus 1 over 2, and then we're multiplying that by a height of 2. So we could leave it unsimplified. I'm going to plug it in the calculator just to see what it comes out to. So I just entered this exactly in the calculator as I see it here. I could probably save some time by not doing 0 plus 1, but whatever. Pressing enter now comes out to -17 over 2, which is really the same as -8.5 if I want to make it a decimal. On this problem, I'm trying to approximate this integral from 0 to 19 of this function that has a few table values represented. And I'm going to use the table with the trapezoidal rule. So I can say this integral is approximately equal to the following. For my first trapezoid area, I've got 5 plus 3 over 2 times a height of 3. So this is base 1 plus base 2 over 2 times the height. And the height in this case is just the horizontal distance from one x value endpoint to the next. So for my next trapezoid, I've got 3 plus 4 over 2 times, this time it's a height of 6. After that, we have 4 plus 2 over 2 times a height of 8 to get from 9 to 17. Then we have 2 plus 4 over 2 times a height of 1. And finally, 4 plus 3 over 2 times a height of 1 again. All right, let me just plug all this in the calculator. So I entered all that in my calculator off camera, making generous use of the alpha y equals fancy fraction mode here. Pressing enter, that's 127 over 2, which if I do math and then decimal, that converts it. That'll be 63.5 if I want a decimal. I don't need one, but I like them, so there we go. On this one, I want the approximation of this integral using the trapezoidal rule with this table of values. So I'm going to say this is approximately equal to, and here's my trapezoid areas now. We have 7 plus 6 over 2 times a height of 3 to get from 0 to 3. So that's my first trapezoid. After that, I've got 6 plus 4 over 2 times a height of, let's see, 3 to 8, that's 5. And then we have 4 plus 3 over 2 times a height of 2. 3 plus 4 over 2 times another height of 2. And finally, we got 4 plus 5 over 2 times a height of 4 to get from 12 to 16. Okay, so I could leave this unsimplified, but I just like plugging things in the calculator, so why not? Here we go. So there's the tail end of all that plugging in using alpha y equals for that fancy fraction mode. Press enter. 153.2, sure, what does that actually equal? Let me do math and then decimal, option 2, and 76.5. All right, I at least know roughly where that is. For this problem, we're given this f function here, sine squared of x over 4 times e to the negative x squared. It's kind of a mess. And it's known that the integral of this thing from 0 to pi over 2 is this weird decimal. We want to use a midpoint Riemann sum of two intervals to approximate this integral. And then we want to know the absolute difference between that and the true value of the integral. So first, let's start by getting our midpoint Riemann sum. And since I'm doing this on the calculator, I'm going to store my answer to this as a constant. I'm going to store it as m. So to get the midpoint Riemann sum, first we need to know what intervals we're dealing with. We're going from 0 to pi over 2. We've got two intervals of equal length, so that means each one must be a length of pi over 4. The interval from pi over 4, what x value am I using for my midpoint Riemann sum? Well, halfway between 0 and pi over 4, I'm going to have pi over 8. So you really need to know your fractions on this one. So I'm going to be doing a base of pi over 4 times f of pi over 8. That is, again, the midpoint of 0 and pi over 4 that I'm plugging into the function to get the height of this rectangle. And the pi over 4 is the base of the rectangle. Next, my second rectangle, going now from pi over 4 to pi over 2, well, that's going to be pi over 4 for the base times f of 3 pi over 4. That's halfway between pi over 4, actually 3 pi over 8, I should say. That's halfway between pi over 4 and pi over 2. So there's what we're plugging in for that second rectangle. Let me actually do that on the calculator now. So if you've entered this correctly in your y equals on the calculator, there's what the function looks like. This is the sine squared of x over 4, but you have to put the square out here. And then we have e to the negative x squared. So quitting out of there, I'm going to calculate basically what I have here now. So let me write all of this out. I've got, let's see, alpha y equals to get my fancy fraction. I've got a pi over 4. And I'm multiplying that by f of pi over 8. To do that, I'm going to do alpha trace, pull up my y1, open a parentheses. Let me get my fraction mode again. And now I'm going to plug in pi over 8. So that's that first rectangle. I'm going to do the next one off camera. So there's the next rectangle with a midpoint sum. And I'm going to set all of that equal, or I'm actually going to store this value now as m on my calculator, or I mean you can pick any letter you want, but I'm going to go to the store button and let me just do alpha, and the division symbol gives me m. Press enter. So this comes out to about 0.0229 and some change. We'll round it off to like 30 if you want. So I need to take this number and figure out the difference between this number and this number up here, essentially. I need to find the absolute difference between m and the integral from 0 to pi over 2 of f of x. So I'm doing this. But, I mean, here's the thing. I'm already using the calculator, so how about I just do all of this on the calculator? So to do this on the calculator and get the most accurate answer possible, I'm going to do alpha window to pull up my absolute value, so I don't even have to worry about that. Then let me do alpha m, so there's my m. I'm going to subtract, now I need the integral, so math 9, from 0 to pi over 2. So here's pi, divide that by 2. And I'm doing that of f of x, which is what I stored in my y1. So alpha trace y1, put a dx there, press enter, and let's see what this is. Okay, that's that weird decimal. That's about 0.0006 and some change. So we'll round it off to 0.00007. 0007. There we go. 0007. And that's going to end up being answer choice A.